Thanks, everyone, and welcome to the Connecticut Water Planning Council's Extreme Weather in Our Watersheds webinar series. This is sponsored again by the Connecticut Water Planning Council, and it's hosted by the Water Planning Council's Outreach and Education Committee. My name is Denise Savageau, and I chair that committee. And we're really thrilled to be able to bring this program to you today. March 22nd is always World Water Day, and this year the theme of World Water Day is saving our glaciers. And although we don't have glaciers in Connecticut, we thought it would be really important to talk about the fact that we are impacted by glaciers, and that's what we're seeing with sea level rise. So we're thrilled to have two speakers with us today to talk about weather and climate change and what is happening, and tying this all together. So we have James O'Donnell. Jim O'Donnell, he's the Executive Director of UConn's Connecticut Institute for Resilience on Climate Adaptation, better known as CIRCA. And he's going to be starting off the presentation. And then we're going to move right into a presentation by Jon Morrison. He's the Long Island Sound Coordinator and the with the Northeast Region U.S. Geological Survey, USGS. And we're really thrilled to have both of these presenters with us today. So thank you for everyone who's attending. Thank you to our speakers in advance. And thank you for to the Water Planning Council for the work that you do and allowing the outreach and education folks to bring this workshop to you. Just gonna ask everyone, please, if you haven't already, mute yourself with your video off. And I'm going to stop sharing my slide and have our first presenter, Jim, share his slides. Thank you.
Okay, I'm going to try and share my screen. Actually, share the presentation. Okay, is it working?
Looks good, Jim.
Okay, great, thanks. So thanks for the invitation. I'm Jim O'Donnell, as I said, and I've been the Executive Director of CIRCA for the last decade. And CIRCA's work is largely to try and help towns and state agencies adapt to the effects of climate change. One of the things that we do is review and try and keep current science regarding what's going to happen, to try and provide information for planning. What I'm going to talk about today is the impacts of global sea level rise on towns in Connecticut. These pictures are from events over the last few years. The Guilford one, none of these are hurricanes. These are all storms that are sort of severe, but of the type that occur every 2 or 3 years. And the ones in Mystic up here happened about 3 years ago. And I think flooding like that in this road by the Mystic River has occurred probably 4 times in the last 5 years. And it's increasing. And that's, I think, a thing that we can do something about. The hurricane threat is slightly increasing, but it's low. And the consequences are pretty substantial. And there's not much we can do about that in Connecticut other than evacuate and try and preserve our evacuation routes and our critical infrastructure. So let me tell you why it's changing. This is a figure that led to some legislative changes in Connecticut 4 or 5 years ago. What it shows is the upper bound of what's likely to happen to mean sea level near Connecticut in the next 100 years. And these lines are different ways of estimating what the upper bound of sea level rise is likely to be. And the blue line, the lowest one, which I'm going to try and point to here, pardon me, is based on data. These two, the orange and the yellow, are based on global models. And this purple line is based on an assessment of what the effects of melting glaciers could be in the worst case. Now, this projection has to be updated at least every 10 years by Connecticut law, and I'm sort of working on that right now. And I'm going to show you some results. The legislation requires that towns and state agencies that are planning infrastructure work in the coastal zone plan for up to 20 inches or 50 centimeters sea level rise by 2050. And that's a thing that has to be evaluated every 5 to 10 years. So the reason it's 50 centimeters is that these are the upper bounds of what's possible, estimated several different ways. And at 2050, they don't differ too much. In the middle of the range is about 50 centimeters or 20 inches. And the other important point about that is that the lowest upper bound, right, is the observation-based upper bound is about 50 centimeters and 2100. So in an important sense, 50 centimeters is what you should do if you're prudent and concerned about climate change in the short run. And it's the least you should do by 2050, because it's very unlikely that sea level rise is going to result in less than 50 centimeters by 2100. So I want to outline what the observation-based data showed in 2017 when I did it. And this is a sort of perspective of Lyell Sound, and the red places are places where there are long records of water level measurements made by NOAA. And if you take the data from those from whenever it started I did this in 2017, so the data ends in 2017. And these lines are the annual mean sea level at all those stations, Bridgeport, New London, and Willets Point. So Willets Point's over here, Bridgeport's in the middle, and New London's in the east. And they all agree really well, and they wiggle around, and they're all increasing. And this is 20 centimeters. This gray stripe is what's called the National Tidal Datum Epoch. It's a 14-year interval, which NOAA uses to define what mean sea level is. Mean sea level is 0, averaged over that interval. If you draw a line using linear regression through the data since 1990 or so, that's what I did in 2017. This black line is what you get. The yellow line was the estimate of global sea level rise rates in 2017. And so clearly we are going up faster than that. And the dashed line, this dashed line here, it bounds all these wiggles. So going forward, the wiggles are sort of built into this, and if the maximum value or the upper bound of what's likely by 2100 then is this dashed line, and by 2050 it's here, it's close to 0.3 meters. Okay, so that's the line I showed here, this blue line. Now, the other way of making estimates of the future is to use models in which we balance the rates of change of energy, momentum, carbon content, oxygen, and we relate how the ocean warms as a consequence of these carbon changes, and how the ocean volume increases by the melting of glaciers in Antarctica and Greenland mostly. And when the ocean warms, the water expands. Just how a cheap thermometer works. It's a column of water in a thin pipe, and when the water in the bulb expands, the water in this thin pipe goes up, right? So when you heat the ocean, it gets thicker, and when you add more water, it gets deeper, right? And both those things contribute to it, and you can calculate how much that happens using a sophisticated mathematics, and that's what this is supposed to illustrate. And so these lines, these yellow and orange lines, were what the IPCC, or the Intergovernmental Panel on Climate Change, it's a UN group, calculated using a wide variety of models in a scenario in which CO2 emissions aren't really suppressed in the coming decades. It's called scenario RCP 4.5. And that's sort of it's not an optimistic, it's sort of a realistic, I think, projection. It's plans for sort of persistent emissions with no real reductions until after 2050. So I think it's the best we can hope for right now. So using that, we get the orange and yellow lines. So the question is, how's that changed in the most recent IPC projections from 2023? And what does recent data show? So here is the most recent data. These are the stations, Bridgeport and London, New Haven, Montauk, and Willets Point, and the data wiggles around as it did before. And what you see here is that these points here are the annual mean water level at those stations in 2024. And obviously it's the highest ever. It's at 0.15, sorry. I'm sorry, I've skipped through it a little. Okay, so here's where the data shows. And then so between 1936 and the middle of the NDTE, that's like 1990 or so, the increase is about 15 centimeters. And since 1990 or so through 2025, it's increased another 15 centimeters, so a total of 30. And there's wiggles, so it may come back down again a little bit next year. And then the reason this is a consequence of this being so high was sort of increased flooding, and I'll show you why. Now, this is the data again on the left, and this black line here is a consensus projection of the analog to RCP 4.5. Now they call it SSP 245. But it's the same kind of emission scenario. Sorry. And this red line, these red bars are the projections for a less optimistic one in which CO2 emissions continue to increase at the rate they've been increasing until 2100. And so you see that in 2050, the upper bound of what's likely this dashed line, this dotted line, sorry, for the 4.5, and it's a little higher under 8.5. And at 2100, the lower bound is again just around 50 centimeters. So the model projections really haven't changed. There's been a slight change in the estimate of how rapidly land is sinking in Connecticut, but that's still a small number, and I don't want to dwell on it because I don't have time. So basically, the projections that we had back then are pretty similar, and this is just a complicated figure showing that. And the outline is this yellow and orange line here should be compared to this dashed line here. So they're almost the same. So the projection at 50 centimeters by 2050 being the upper bound for planning purposes is still the same. Now, why does that make a difference? I want to show you now exactly why. This is sea level observations at New London in last year. The green being the observations and the blue being the tidal variations, that is the predictions of the fluctuations due to the tide. And the difference between those two things is due to the weather, due to storms. And if you plotted the difference between those two things for the last, back to 1938, that's what this blue line shows. And these are all due to the weather disturbances that have occurred in the last 100 years or so. And during that time, the water got above 4 feet, or the surge got above 4 feet 5 times. Had the weather been the same and the mean sea level was 20 inches higher, then the data would look like that. Instead of just exceeding 4 feet 5 times, it would exceed 4 feet 48 times. So a 20-inch sea level rise leads to a 10-fold increase in flooding at 4 feet in New London. So that's pretty profound, and it demonstrates simplistically how mean sea level can cause a significant change in flooding risk. Now, we have long data at New London, and a few other places, but we need projections for what's going to happen at lots of places in Connecticut. And so we did a model a while ago which simulates a whole bunch of storms and predicts what the water level would be at lots of places in Connecticut. And I'm going to show you the results of that now. This is the result for New Haven, and this is a new result for New London, and this is called the return interval diagram. And it basically shows what the probability is of storms, of surges of different heights. And so, for example, here, this point would be, it would be about 2.5 meters at New Haven, and it would anticipated return interval of 70 years, or the probability each year is 1 in 70. And back here, this is a probability of 1 in 10. That's a 10% per year probability, and that's about 2.2 meters. And these blue lines are a separate analysis from the Corps of Engineers. But what I want to point out is, although the Corps is a little more pessimistic, the slope of the line is the same. Now, the reason way you can use that is that if you know now that the 10-year return interval is like 2.3 at New Haven, and if mean sea level increased 20 inches, then this blue line and the orange curve become the green dashed line. And so then you could see that 2.3 meters would in New Haven would have a return interval of 3. So there it would be a 3-fold increase in risk. So my point being that the mean sea level increases the risk of flooding substantially, and it varies from place to place. This is a map of what the 1 in 10-year flooding risk, what a 1 in 10-year risk flood in Mystic would look like. And the colors here are represent the depth of water over the land. And this is a result of a simulation which is quite detailed, and the model is verified by observations as best we can. And what it shows is lots of the area of Mystic, which is an important southeastern Connecticut tourist destination. And over here, there's quite a lot of historical important housing. They're going to be flooded by up to 2 or 3 feet of water during a 1 in 10-year event in 2050. So there's my summary. Annual mean sea level was highest ever in 2024. The look for 2050 looks pretty much the same as it did in 2017. That is as much as 20 inches or 50 centimeters of increase by then. The higher mean sea level is going to cause coastal flooding at all levels, and that's flooding should be expected more often, and consequently, cost of repairs and insurance, etc., should be anticipated going up. Vulnerability of towns is very site-specific. It depends sensitively on the geometry. For example, in Mystic, there's the railway crossing and a narrow bridge. Other towns have got different details, and those things make a difference to the occurrence of flooding and what you do about it. So that's my presentation. I'm happy to take any questions when appropriate.
Thank you, Jim. We're going to hold questions to the end. If people can put questions in the chat, but we'll also ask you to raise your hand. So thank you. We're now going to have Jon Morrison talk about the gauges that we have and how important that is for collecting all of this data and talking about extreme weather events. So thank you.
Okay, Jim, you got to stop sharing. There we go. Okay, can you see my slides, Denise?
Yes, we're good. Thank you.
Okay, great. So thank you for your time this afternoon to talk about the USGS stream gauging program. The USGS stream gauging program began in about 1879 in the United States and has various periods of record throughout the country. A stream gauge looks like this little structure down here in the inset image. And many of you have probably driven by some of these along the roads of Connecticut. They're located all over the place. So the value of long-term records, and I want to point out here, this is a very important curve about long-term monitoring records. And this curve over here on the right is based on the continuous CO2 measurements at the Mauna Loa Observatory. And these were started by Charles Keeling in the 1960s to look at seasonal changes in CO2. And through the course of that project, he realized that CO2 concentrations not only changed seasonally, but were also increasing throughout time. And his quote here is that the only way to figure out what is happening to our planet is to measure it. And this means tracking changes decade after decade and poring over the records. And that's really what long-term monitoring records need. And Jim pointed out some information about long-term records and the data that were used in his analysis. and the value that these data provide. Without long-term monitoring data, we really can't answer the questions of tomorrow without the data that we collect today. So what do stream gauges do? Here in the image on the left is the Yantic River at Yantic, Connecticut. This gauge was in the news quite a bit last year. And the gauge is all the way in the back, the little greenhouse back there. And the foreground is a field that we usually use to access the gauge. The river is actually behind the gauge in amongst the trees. And last March, the river stage got pretty high. And so what does the gauge do? It measures the height of the water in the river. And so this gauge has been around for nearly 100 years now. And right now we can look at the information in the real-time webpage, and we can see that the stage is just under 4 feet, and that's the height of the river. We call that stream stage or gauge height. But last March, on the 23rd, the river stage was up over 9.6 feet, which these two lines here indicate from the National Weather Service what the flooding conditions are. And so above 9.5 feet is considered moderate flood stage. Some of my colleagues at the DEP spent some time last spring standing around the banks of the Yantic River with lots of news coverage talking about whether a dam upstream was going to fail. And if that dam had failed, there could have been significant flooding downstream, could have gone to major flood stage. Luckily, the dam held, and we did not have that happen. Oops. So not only do stream gauges provide information on gauge height or stream stage, they also provide information on stream flow. And to do that, we have to have our hydrographers go out into the field and make measurements. And they make measurements of the stream flow that they can then relate to the gauge height of the river. And then we can produce that stream flow record. And here's an image in the upper left of a gentleman making a stream flow measurement, probably back in the 1920s. The equipment that he's using there was equipment that I used when I started my career here 38 years ago. Now we actually use equipment down in this lower left image, which is we have one of our hydrographers towing an acoustic Doppler current profiler back and forth across the river, collecting data on his laptop. And the image of the stream flow is actually shown here on the right-hand side. This is what the data looks like when it comes in. So we get much more accurate data, and it's a lot easier for our stream gaugers to collect that information. So here's a rating curve, and this is how we translate gauge height information or stage to discharge. So the y-axis on the left is the stream stage, and the x-axis here across the bottom is the discharge. And so we go out periodically throughout the year, and we make measurements of both stream stage and the correlated discharge at that time. And so we plot those up, and that gives us this rating curve. And the rating curve allows us to use all the continuous stream stage that's measured to predict what the actual stream flow was in the river at the time. So the uses of stream gauging information. We can use information from stream gauges on flood forecasting. So here in the upper left panel, in real time, we can use that information that comes from the gauge about the height of the river. And the National Weather Service can use that information for any of the sites that they make forecasts for, predict whether or not the river is going to go over a warning stage or into flood stage, how long it's going to be there, and what the actual height might be. You can also use it for reservoir operations here in this dam picture on the lower left to let reservoir operators know that there's a lot of flow coming down towards them and that they need to change their operations to accommodate that. You can also use it in floodplain mapping, so the height of the river can be applied to the topography, and we can look at how high the flood will be across the landscape. And that stream flow information can be used for engineering design. We can determine whether or not a bridge will be able to pass a certain flow, or in this case, possibly fail. We also use our stream gauges to document extreme hydrologic events. The image on the left is the Deerfield River above West Deerfield. This is tributary to the Connecticut River. This is after Tropical Storm Irene. You can see that the river is transporting quite a bit of sediment, and that this is an extremely high flow here coming through this valley. And on the right-hand side, another extreme event. Here's the Segregansett River back in September of 2020. This is a tributary into Narragansett Bay where we were doing a study, and the stream actually dried up. and was dry for a significant period of time during that time. So the USGS stream gauging network nationally consists of over 8,500 stream gauges across the 50 states, Puerto Rico, and the Virgin Islands. And there's a link here that can take you to that resource. New England-wide, there's over 350 stream gauges in the New England area. And this link here will bring you to a multimedia presentation on how useful stream gauges can be. So the stream gauging networks are really a network of network. It's a multi-objective network. So we have gauges that are installed to measure high flows. Some are more focused on low flows. Some are focused on regulatory needs and compliance, long-term statistics, annual peak flow information, the real-time information that comes from the stream gauges, water management issues. Recreational users have now tapped into the streams and used that information quite a bit, as well as the engineering design. So in the lower right-hand image is a picture of the Byram River near Greenwich, which is one of Denise's favorite gauges. Okay, so the USGS stream gauging program, the USGS national page has quite a bit of information about how these gauges work and how the program works itself. In this image, you can see me back in 2005 determining that the water is actually too deep for me to make it to the gauge on the Mount Hope Brook during this fall flood that we had. So the stream gauging network is supported in part by the federal priority stream gauges. The federal priority stream gauges has focused its needs based on forecasting floods, droughts, and other stream flow related issues, to support water quality assessments of major rivers and estuaries, support interstate and international compacts, court decrees, treaties, and other water body border water agreements, to track stream flow in the major rivers and contributions from key basins to the next downstream basin, estuary, ocean, or the Great Lakes, and to describe long-term trends in stream flow at sentinel sites that typify major ecoregions, river basins, including trends related to population, land use, water use, and climate. And in order to do that, you need a fairly dense network of stream gauges. So the federal priority stream gauge mapper is included in the link below. And if you click on that link, it will take you to all of the gauges that are supported in part or in total by the federal priority stream gauges, which is only a small fraction of all of the gauges that are operated in the United States. The distribution of stream gauges across New England. Here you can see the real-time imagery. All these colored dots indicate what their flow conditions are. So any of these sites, you can click on these dots and it'll take you to the specific gauge. And the colors are actually attributed to what the flow conditions are. So the map on the right shows you what the graphic is displaying. So the red and warmer colors show you that those are low flow conditions. The dark blue and dark black conditions indicate that those are high flow conditions. And so with a real quick snapshot, you can see what flow conditions are going on across the whole region, and you can focus in on any of the areas that you're interested in. And one other thing to note is that the image on the left, you'll see that many of the gauges around here are black, but there's a couple of orange ones underneath. And those are probably regulated basins that are able to hold back those high flows and only discharge a certain amount of flow downriver, showing how variable some of the stream flows can be. In New England, stream gauges are funded through a variety of partnerships. The USGS Federal Priority Stream Gauges is part of that funding. We also rely on funding from the US Geological Survey Cooperative Funds, the US Army Corps of Engineers, the Federal Energy Regulation Commission, US Environmental Protection Agency, the states of Connecticut, Massachusetts, Rhode Island, New Hampshire, Vermont, Maine, various water companies, and local partners. So these programs are leveraged from the stream gauging network. So with all of that information about stream gauging, we can begin to do analysis, either at the state level or at the regional level. And we can do flood frequency analysis, which is really important. How often do floods of a certain magnitude occur? Low flow frequency analysis, which allows us to do the same thing, only looking at low flow conditions, and the probability of drought. Regional analysis that use consistent methodologies across the areas are really important because they help reduce errors and cut down on the amount of overlap in the analysis. We also can develop a program called StreamStats, which is an application that runs on the USGS webpage, which allows a user to go in, define a watershed area, and if it's gauged, it'll get the information from the gauging. If it's not gauged, it'll provide information to the user on what potential stream flow statistics could be for that watershed based on correlated stream gauges in the area. We can also use the information to look at flood inundation tools in real time, so we can develop real-time flood mapping. We can work with the National Weather Service on flood forecasting information as well. In Connecticut, the stream gauging network looks basically like this. And you can see that the pink is all the watersheds that have that are gauged. And across the southern tier of Connecticut, there is a substantial amount of the area that is ungauged. And a lot of these are because they're either very small brooks or they are tidal up through these areas as well. In Connecticut, the stream gauges are funded by a variety of different sources. And we kind of talked about that briefly. With the Connecticut DEEP providing the funding to support the most of them, as well as the USGS through a variety of its programs, the Army Corps of Engineers, and then water companies providing a lot of that funding as well for water planning purposes. Stream gauges by length of record is really important for us to have long periods of record to look at the recurrence interval of long-term floods. If we want to talk about a 100-year recurrence interval flood or a 500-year recurrence interval flood, it's hard to do that when we have a network of stream gauges that only has 30 years worth of record. There will be a substantial amount of uncertainty in those projections. So these long-term record gauges are really, really valuable to us because they have almost 100 or more years of record. So you can see from this plot that we have almost a dozen stations with 100 years of record, and that's a pretty good number for us. However, those are mostly focused on very large rivers, and if you look at the rest of the distribution, we have gauges, a number of gauges with less than 30 years worth of record, and so we need to continue to operate all these gauges to answer specific questions. So one of the issues that we have is that we don't really have a lot of gauges with in small watersheds, 10 square miles or less. So the y-axis here is the number of gauges, and then the bins here are drainage areas. So with 1 to 10 square miles, we only have about 9 stream gauges in that range. We have many between 70 and 200 square miles, and the other bin of 20 to 70 square miles. So this range we have pretty well. And then the larger watersheds, well, we have those gauged. So that we think we've got the information we need from some of those larger watersheds, like the Connecticut River, the Quinnebog, the Shetucket, and the Housatonic Rivers. Those gauges have been around for a long time. If we look at land uses by major basin, we can see that the Quinnipiac watershed has the highest median developed land percentage, about 41%. And then the lower Connecticut River is next, and the Saugatuck River here down at 46%. So we look at the distribution of our gauges across those major land uses because they contribute to the amount of runoff that is generated during specific events. Our priority science gauges that are needed really are in unregulated watersheds, small watersheds, less than 5 square miles, heavily urbanized watersheds, high elevation watersheds, and steep slope watersheds, because we don't feel we have enough records here to really help generate good statistics on what the recurrence interval is for some of these storms. The role of extreme events. Extreme events usually control the upper ends and lower ends of our measurement range. These values can impart significant leverage on relations being explored. It can also constitute the areas that measurements are hardest to obtain and therefore have increased uncertainty. Here's an image from the Naugatuck River from the Great 55 flood. And trying to actually get a discharge measurement during that period of time would have been quite difficult since the flooding extends from bank to bank across the entire channel. In real time, here's an image from 2010, Pendleton Hill Brook. Our crews couldn't get out to actually measure the gauge because many of the roads were flooded and there was no access. And so here you can see on the image on the right, the road is unpassable. Perhaps they could make it to the stream gauge through the Zodiac, but they certainly can't drive to the gauge. Other issues are making sure that the gauges are operating throughout the range of the flow. Here's an image on the left at the Willimantic River in Coventry in 2005. When I first got to the gauge, this is after making a measurement, the water was all the way up to the door. You can see the high water mark here, and that the flow had actually come into the gauge, and the gauge was underrepresented because the float that runs the gauge was hitting the floor. Here's the Farmington River in 2007, again, making access to the gauging structure quite difficult. So when we look at modeling annual exceedance probabilities for these floods and trying to determine what a 100-year flood is, which would be a 1% annual exceedance probability, we plot up all the peak flows, annual peak flows, what was the highest flow that we got for the station for the year, and we plot that across a probability distribution. And then we extrapolate that line and look at what we think the 1% probability would be. And so we take that up to the line, and then we correlate that back to the flow. And we'd look at the 100-year flow here at the Little River at Hanover is approximately 2,860 cubic feet per second. Well, that's a pretty high flow, and that would be very hard to measure out there. So there is some uncertainty in this projection. You can see that the confidence intervals kind of open up on this projection at the very high end as well as the very low end. Here's determining recurrence intervals for Bunnell Brook. Here's a 2-year period from January 2010 through January 2012. And you can see the green line is the 2-year recurrence interval. And we had somewhere in the neighborhood of about 12 2-year floods during this period of time. We also had 4 10-year recurrence intervals in less than a year's time here as well. So just because we had the flood once in the 10-year flood doesn't mean that it's going to be 10 years again before we have another 10-year flood. We can have them a week apart. In this case, we did right here. So what drives a lot of the flooding are changes in the long-term precipitation. So the stream flow statistics have changed throughout the long periods of record. Here in around the 1970s, there was a step trend in the amount of precipitation that is received in Connecticut. You can see that the bottom of the wiggliness of the curve has basically gone above 45 inches per year. Whereas prior to that, we had a fair amount of years above and below it. Most of these years now are above that. So why aren't flood increases as big as heavy precipitation increases? Well, it's not just about the heavy rainfall. So sometimes we get precipitation that falls during our dry season, so we can get very intense rainfalls in the summertime when the antecedent conditions or the conditions on the ground are very low flows, low groundwater levels, and dry soil conditions. So they don't necessarily correlate. So a 100-year rainfall event does not necessarily correlate to a 100-year runoff event. However, we are starting to see changes in that distribution of rainfall. Our falls are getting wetter, and they are starting to have significant impact on the changes in our flood recurrence intervals. Here's an image from Hurricane Harvey. The image on the left is precipitation, and over the course of about 4 days, they got over 30 inches of rain related to that hurricane system. And one of our colleagues that worked in Connecticut had just transferred to the Texas office and was running their stream gauging network during that time period. And here's the information from the stream gauge. And the stream gauge went from about 4 feet to over 35 feet. And at 35 feet, the gauge went underwater. So even though we have these stream gauges, we don't necessarily have them built to withstand some of the extreme changes we're starting to see in some of the rainfall, resulting in extreme flooding. So hardening of these gauges after a period of time now is really important. And why are these precipitation increases happening? Warm air can hold more water, and that excess water in the atmosphere can come out intensively in these rain events like we saw in Harvey. In August in Connecticut, we also had a fairly intense rainfall, about 10 inches in under 12 hours. Some bases got more than 10 inches. USGS had 7 stream gauges in this area, with watershed areas that range from 15 square miles to about 1,500 square miles. The annual exceedance probability ranged from between 100 to 200 year event to 25-year event. And so the small watersheds, this was a very significant event, 200-year event for a small watershed about 15 square miles. Our larger watersheds, because the rainfall didn't cover the entire watershed area, it wasn't as big an event. So this 25-year event was from the Housatonic River at Stevenson, which is represented by this 1,500 square mile drainage. And then during this event, we had 1 stream gauge destroyed. The Putatuck River at Sandy Hook was actually overtopped, and the gauging equipment was lost during this event. And we also had numerous roads affected by bridges and culverts failing throughout the storm. So follow-up to get out there to inspect the gauges and do work was quite difficult. And NOAA has a very nice story map of this event on their webpage, and the link is included here below. So that's all I have to present. Thank you. And thanks to all of our valuable USGS cooperators that help support this valuable program and keep it running.
Thanks, John. And I do have that favorite gauge in the Byram. I used to work in the Emergency Operations Center for the town of Greenwich, and my job was to look at gauges. So, and it came really handy. And the interesting thing is our neighborhood association in that area learned how to read that gauge because it's online, and they had a network where they would talk to each other and say, hey, the gauge is at this stage, and let everybody in the neighborhood know when they needed to bring out the sandbags, when they needed to move their cars, when they needed to do whatever they needed to do. So really, really important tools on during emergency events, but also for the long term, making sure we have that long-term information. So thank you. We have a couple of questions in the chat, and also if anybody wants to raise their hand, that would be also okay. So I think we've got one question we can start with. Allie, you going to read the questions for me?
Sure. First of all, thank you, Jim and John. That was a great presentation. I learned a lot. So the first question is from Alicia, and Jim, I think this is for you. Is CIRCA looking at other impacts besides sea level rise? It's very difficult to get those outside of coastal communities to understand how climate change will impact them and how our activities inland can make local flooding much worse when the focus is solely on sea level rise. Yet inland communities such as Southbury and Oxford are already feeling these impacts.
Yeah, so we're doing quite a lot of work in inland communities too. I just focused this presentation on sea level rise because that's what I'm working on right now, and Denise invited John to talk about precip. But the 3 things we're working on really. One is coastal flooding. Second is inland flooding and what to do about it. And the third one is what's the science associated with predictions of future changes in air temperature, precipitation rates, and sea level rise. And so, we're definitely interested in those things.
Thanks, Jim. And in defense of Jim, because of the tie-in to World Water Day and glaciers, we specifically asked him to tie into that sea level rise here, even though we know CIRCA is looking at all of these. Allie, do we have another question?
Yes, John, I believe this question is for you from Virginia. Please discuss the lack of stationarity as it relates to climate change.
Sure. So stationarity is a concept that basically the premise is that if you collected 30 years worth of record, that you would have accounted for most of the variability you would see in a system, and that the statistics that would be generated from that 30-year period would be applicable to longer ranges and could be extrapolated out. However, what we saw is in that 1970 step trend in precipitation, we also see that step trend in stream flow as well. And so the concept of stationarity is that things are possibly changing and that we might need longer periods of record to help us understand the variability in the record. And so we need longer and longer periods of record to understand that because things are actually changing. The cycles are much longer than what we thought. They're certainly longer than 30 years. They could be 100 or 500-year cycles that we need to get the statistics for to be able to predict robust recurrence intervals for.
Can I comment on that too?
Sure.
Yeah. So I agree with everything John said, and I also want to point out that the geology mantra is that the past is the key to the present, right? But we don't have any past conditions, any observations on past conditions like those we expect to see in climate in the future. So we have to rely upon simulations that are capable of simulating things we have seen, so that we can project things that we haven't seen in the future. And those, unfortunately, our capacity to do simulations of future weather are really limited. And that's one of the things that we're going to be including in our report this year on changes in precipitation patterns.
Thanks, Jim. And the question I had is just a follow-up to that is, and we've been talking about this at the Water Planning Council when we talk about water supply, is having a long range. So looking at a rolling average so we've been looking at a rolling average in terms of, water supply and drought and those types of things, but also looking back the 100 years. But if we're having changes in precipitation rates and we're really looking at that quantity of water, does it make sense for us to continue to look at that long range where it may be smoothing out that rolling average, or would it be better for us to, and sometimes look at a shorter period? So just thoughts on that.
John.
We don't want to make it easy for you.
I'll start with it, I guess. So it's always been my opinion that you use the longest period of record possible. Shorter periods can give you a lot of variability. So if we looked at precipitation at 30-year intervals throughout the entire 120 years or 30 years that we have record for, you would see that those 30-year averages would have quite a bit of variability around them. So short periods of time, short windows of time, can give you somewhat misleading answers, I think. So the longer period of record is, I think, a much better thing to be looking at. And when you start to average, you start to smooth. And if you're looking for extreme events, you're not going to find it through smoothing. You really need to look at the frequency of the extreme events and how often they're occurring. And so that can't really, it's not done well by smoothing the data through averaging.
Yes, so I think that's true that's true, right? But that's most relevant for flooding issues. But I think Denise is concerned about water volume as well, and so there we're not so much concerned about predicting extreme events effectively, because an extreme event, though damaging, may only be 5% of the total volume delivered to Connecticut in the year. If it all happens in one day, it's bad news. But for drinking water supply problems, I think we can look forward with climate models with those, because they're relying. What we're trying to predict is a little easier. We can do a better job with things like the mean annual precip than we can with the extreme event magnitude.
Thanks, Jim. Allie, do we have a next question in the chat?
Yes, and this question's for John. Big question. There has always been a threat to funding for stream gauges. Has this threat increased in the past few months?
The funding uncertainty has always been with us when we run the stream gauging program. Right now, it's no different than any other year. A lot of the funds come from the federal government. And if they don't come from the federal government, they do come as federal government funds that are passed through by the state. So we are concerned about the funding levels. We have tried to diversify the funding to support the gauges in as many different ways as possible. So you saw that big long list of cooperators that help support those gauges. But the real scientific need gauges are the ones that don't have advocates like water companies paying for them. And so the gauges that we do science with that are unregulated basins, that don't have water diversion issues associated with them, that are small watersheds, those are the ones that are really important to us. And those are the ones that are very hard to advocate for funding from other sources. So if there's changes in the state funding structure or the federal funding structure, that's an area that's extremely vulnerable to us. So yeah, we're quite concerned about it.
Thank you. Catherine from West Hartford says, our town sustainability commission would like to get the town to focus more on this, but keeps getting passed around between other things such as public works, engineering, parks, emergency operations. Do you have any ideas of where and how the sustainability commission can start? And this question might be for either of you.
I'll kick that to Jim.
Good one, John. You learn quickly. Yeah, so this is a common problem, right? And it's true at state agencies too, that these challenges that arise from the effects of climate change span the authorities of several different offices. And sometimes the priorities that have been established in the past are the focus of the staff in those programs. And so things that are not their focus end up being deprioritized. So what I recommend, and I think this is what Groton has done where the town where I live, is they create a sustainability office hire someone whose job it is to do that. And it's awkward because they have to now fit in the ecosystem that has evolved in their town management system. But it's the only way that I think that a sustained attention to these problems, which take a long time to address, can be maintained.
Thanks, Jim. And I just want to add in, and one of the reasons I got so involved in water is the Conservation Commission, by statute, is charged at looking at water resources in your town. And as the Conservation Commission, not some conservation commissions also serve as inland wetland commissions, but if they don't have that role, they can really play this role that brings land use planning and looking at land use and watersheds into that managing for public works and planning and emergency operations department. It's actually how I ended up serving as the conservation director, serving in my emergency operations center, because I understood the role of the gauges and whatever. So, from a land use planning perspective. So just putting that out there, I think having a resiliency office is genius. We kind of started putting that together in Greenwich as a team between our land use and our emergency operations, and bridging that gap is really, really important. So a couple of ways to do it, but it's a great question. Before we get into any more questions, the one thing I wanted to make sure when we have just a few more minutes is, could you just one more time talk about what is a 100-year storm event versus the percentage and how those happen? Because I think that is probably one of the most confusing things for everyone.
Yeah, so let me take a stab, right? So if you roll a dice, you've got a 1 in 6 chance of getting a 6, right? And you should expect on average to get a 6 once every 6 rolls. But it doesn't mean you'll get 6 every 6 rolls, but it's likely that you will. And so the same is true with storms. The 1 in 10 storm has a probability each year of 10% of occurring. And the probability of getting 2 10-year return or 10% risk storms in 1 year is 1 over 100. It's the square of those two things. So it's just like rolling dice, whereas the number is 1 in 6 for any number that you choose on the face of a dice.
John, do you want to add into that?
No, I think Jim explained it pretty well. So it's a probability. And so it is the statistical probability that the event will occur. And so a flow of a certain magnitude or a rainstorm of a certain magnitude has a 1 in 100 chance of occurring. And so that's what the annual exceedance probability is designed on. And it can be confusing. So we call that a 1% event, but what most of the way it's expressed is it's a 100-year flood. And we've moved to annual exceedance probability to describe it based on the fact that it's a probability instead of the 100-year flood, because people were confused by the 100-year flood, saying, well, we just had a 100-year flood. Why are we having another 100-year flood? 100 years hasn't gone by. It does not mean that that is a time interval. It's a probability.
Yeah. What every year, you know, 1%. And yeah.
And then a
Exactly.
lower the 10% return interval is a lower level, right? So in New London it's about 2.3 meters. The probability of getting that value or higher is 10% per year. And so in your lifetime you'll probably see multiples of those, but your chances of seeing a 100-year event in a 40 or 50-year lifespan is only like 50%, right? So many people haven't seen a hurricane in Connecticut.
Allie, you have a last question as we wrap up?
We're all set. I don't see
Okay.
any new ones.
Oh,
Okay.
cool.
Well, I want to say thank you to our speakers again. And I just wanted to also say that we are going to be continuing on with this webinar series. We're going to be looking at talking to foresters about wildfires, and we're looking at the impacts, because this is coming from the Water Planning Council, the impacts of extreme events and water on water quality, not just quantity. We focused a lot on quantity issues today, but we're also going to be looking at, well, what are all these extreme weathers, you know, what's the impact on water quality? So stay tuned. We'll be looking at another workshop later on this spring and probably one in the fall, and we'll be sending that information out. Again, thanks to our speakers, and thanks for everybody for joining us. Have a good day, everyone.
Thank you.
Thank you.